close your eyes for a moment if you can. Imagine waking up tomorrow morning, and when you open your eyes, you do not see sunlight. You do not hear birds. You do not feel a breeze coming through your window. Instead, you see a metal ceiling, a grey, cold, utilitarian metal ceiling that hums with the vibration of machinery. You get out of bed, and your feet touch a metal floor. You walk to what should be a window, but it is not a window. It is a screen. And on that screen, there is an image of a sky. A fake sky. A simulation. A reminder of something you have never actually experienced. You have never felt rain on your skin. You have never stood in an open field and looked at the horizon. You have never seen a sunset with your own eyes. You have never smelled the ocean. You have never heard thunder. You were born inside this metal structure. You have lived your entire life inside this metal structure, and you will die inside this metal structure. And here is the part that should genuinely disturb you. You did not choose this. You did not sign up for this. You did not volunteer. Someone who died 100 years before you were born made this choice for you. Someone who never met you, who never knew your name, who could never have imagined your face, decided that your life would be spent inside a machine, hurtling through the emptiness of space at unimaginable speed toward a destination that you will never reach. You are a link in a chain, a means to an end, a biological stepping stone for a goal that belongs to people long dead and people not yet born. Your entire existence, from your first breath to your last, serves one purpose and one purpose only: to keep this ship moving, to maintain the systems, to have children who will maintain the systems after you die, and their children after them, and their children after them, until one day, maybe 200 years from now, maybe 500 years from now, maybe 1,000 years from now, a generation that you will never know, that will never know you, that will probably not even remember your name, will step off this ship and onto the surface of a new world. That is a generation ship. That is the concept we are talking about today, and on the surface, it sounds like one of the most beautiful, most ambitious, most inspiring ideas humanity has ever conceived. A ship that carries an entire civilization across the stars. A vessel so large, so complex, so self-sustaining that it is essentially a world unto itself. A mobile planet. An ark of humanity sailing through the cosmic ocean to plant the seeds of our species on a distant shore. Poets would write about it. Filmmakers would dramatize it. Scientists would dream about it. And they have. For over a century, some of the greatest minds in human history have thought about generation ships. They have designed them. They have calculated their trajectories. They have debated their feasibility. And the more you learn about them, the more you realize something profoundly unsettling. The idea is beautiful. But the reality, the actual, practical, lived reality of what a generation ship would mean for the human beings inside it, is nothing short of horrifying. And today, we are going to explore every single dimension of this concept. We are not going to skim the surface. We are not going to give you a 10-minute overview and call it a day. No, today, we are going deep. We are going to talk about the physics, the engineering, the biology, the psychology, the sociology, the philosophy, the ethics, the history, the science fiction, the real scientific proposals, the catastrophic failure scenarios, the alternatives, and ultimately, the question that sits at the heart of this entire discussion. Should we do it? Can we do it? And if we can, does that mean we should? This is going to be one of the most comprehensive explorations of generation ships that you have ever encountered. So if you are the kind of person who loves space, who loves science, who loves thinking deeply about the future of humanity, who loves having your mind expanded and your assumptions challenged, then you are in exactly the right place. Hit that subscribe button right now, smash the like button. and I want you to drop a comment before we even get started. Here is your question. If someone came to you today and said, "We are launching a generation ship to another star system, the journey will take 300 years, you will never reach the destination, but your descendants will," would you volunteer? Would you step onto that ship knowing that you are giving up the earth, the sky, the wind, the rain, everything you have ever known, forever? Think about that. Really think about it. Write your answer in the comments. I will be reading them. Now let us begin. Before we can understand why generation ships are so terrifying, we first need to understand why they are necessary. And to understand that, we need to confront a fact that most people do not think about in their daily lives. Humanity is trapped. Right now, as you watch this, every single human being who has ever lived, who is currently alive, and who will be born in the foreseeable future, exists on a single rocky planet, orbiting a single medium-sized star in a single galaxy among trillions of galaxies. Every piece of art ever created, every scientific discovery ever made, every war ever fought, every love story ever told, every civilization that has ever risen and fallen, all of it happened on one planet. Earth, and Earth, for all its beauty, for all its abundance, for all the ways it has nurtured and sustained us, is a death trap. Not today, probably not tomorrow, but eventually. Inevitably, this planet will become uninhabitable. The question is not if, the question is when. And the question is whether humanity will still be here when it happens, or whether we will have already destroyed ourselves. The threats are real, and they are numerous. Asteroid impact. It has happened before. 66 million years ago, a rock roughly 10 kilometers across struck what is now the Yucatan Peninsula in Mexico, and it wiped out 75% of all species on Earth, including the dinosaurs. It will happen again. The question is when. Supervolcanic eruption. The Yellowstone caldera in the United States sits atop a magma chamber that, if it erupted at full force, could blanket the continent in ash and plunge the planet into a volcanic winter lasting years, potentially decades. Global pandemic. We got a taste of what a pandemic can do with COVID-19, and that virus, terrible as it was, had a relatively low mortality rate. Imagine a pathogen with the transmissibility of measles and the lethality of Ebola. Nuclear war. For decades, humanity has possessed the capability to destroy itself many times over. The weapons still exist. The tensions still exist. Climate change. A slow burn, but potentially just as devastating over centuries. And then there are the cosmic threats that we cannot even see coming. Gamma ray bursts. Rogue black holes. Solar flares of extraordinary magnitude. The gradual brightening of our sun, which will eventually render Earth uninhabitable in roughly 1 billion years, long before the sun itself expands into a red giant and quite literally swallows our planet. Stephen Hawking, one of the greatest physicists who ever lived, said it plainly. He said that humanity must leave Earth within 1,000 years to ensure our survival. Some scientists think even that estimate is generous. The point is this: if we are serious about the long-term survival of the human species, and I mean genuinely serious, not just philosophically serious, but practically serious, then we must become a multi-planetary species, at minimum, and ideally a multi-stellar species. A species that does not depend on one planet, one star, one solar system for its continued existence. A species that has spread far enough, wide enough, that no single catastrophe, no matter how vast, can wipe us all out. And this is where the dream begins. The dream of interstellar travel, the dream of reaching other stars, other planets, other worlds where humanity can plant new roots and grow. It is a magnificent dream. It is perhaps the grandest dream our species has ever dared to dream. But here is the problem. here is the thing that separates this dream from every other great human achievement. The distances involved are not just large. They are incomprehensibly, absurdly, almost mockingly large. When we talk about interstellar distances, we are talking about numbers so vast that the human brain simply cannot intuitively grasp them. We can write them down. We can calculate with them. But we cannot truly feel them. Let me try to help you feel them. The nearest star system to our own is Alpha Centauri. It is a triple star system consisting of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, a small red dwarf that is actually the closest of the three to us. Proxima Centauri is approximately 4.24 light-years away. That means that light, travelling at approximately 300,000 kilometers per second, the fastest speed possible in our universe, according to everything we know about physics, takes 4 years and 3 months to travel from Proxima Centauri to Earth. Now, let me put that in more familiar terms. Light travels at about 1.08 billion kilometers per hour. In 1 year, light covers approximately 9.46 trillion kilometers, so 4.24 light-years is roughly 40 trillion kilometers. 40 trillion kilometers, let me try to make that tangible. If you got in a car and drove at 100 kilometers per hour, 24 hours a day, 7 days a week, without stopping, it would take you approximately 45 million years to reach Proxima Centauri. If you took a commercial aeroplane flying at 900 kilometers per hour, it would take roughly 5 million years. The Voyager 1 spacecraft, launched in 1977, is the fastest object humanity has ever sent into deep space. It is travelling at about 61,000 kilometers per hour. At that speed, it would take Voyager 1 roughly 73,000 years to reach Proxima Centauri. 73,000 years. For context, 73,000 years ago, Homo sapiens had not yet left Africa in large numbers. The entirety of recorded human civilization, every empire, every religion, every war, every discovery, fits within the last 5,000 to 6,000 years. Voyager would need to travel for roughly 12 times the entire span of human civilization to reach the nearest star. And Proxima Centauri is the nearest star. Most of the interesting exoplanets we have discovered are much, much farther away. The TRAPPIST-1 system, which contains 7 rocky planets, 3 of which orbit in the habitable zone, is roughly 39 light-years away. That is almost 10 times farther than Proxima Centauri. Kepler 442b, one of the most Earth-like exoplanets we have found, is roughly 1,200 light-years away. At Voyager 1 speeds, reaching Kepler 442b would take approximately 20 million years. So here is the fundamental problem. We cannot go fast enough. We simply cannot. Not with current technology. Not with any technology we can reasonably project for the next several decades. And the reasons for this are not just engineering limitations. They are rooted in the fundamental laws of physics. Einstein's special theory of relativity tells us that as an object with mass accelerates toward the speed of light, the energy required to continue accelerating increases exponentially, approaching infinity as you approach light speed. You cannot accelerate a physical object to the speed of light. It is not a matter of building a bigger engine or finding a better fuel. It is a fundamental law of the universe. The speed of light is a hard wall, and no amount of engineering can break through it, at least not with any physics we currently understand. So if we cannot travel at the speed of light, how fast can we go? With current chemical rocket technology, the kind of propulsion that got us to the moon, we can reach speeds of perhaps 40 to 60,000 kilometers per hour relative to the sun. That is pathetically slow for interstellar travel. Even with more advanced propulsion concepts, nuclear fission, nuclear fusion, ion drives, solar sails, the projected speeds for a large, heavy spacecraft carrying human passengers max out at perhaps 1 to 10% of the speed of light. Let us be generous and say we achieve 10% of the speed of light. That is 30,000 kilometers per second. An extraordinary speed by any human standard. At 10% of light speed, reaching Proxima Centauri would take approximately 44 years. That is a single human lifetime. You could leave at age 20 and arrive at age 64. Tight but conceivable for a single generation. But here is the catch. Achieving 10% of light speed for a massive spacecraft is, with current and near-future technology, essentially impossible. The energy requirements are staggering. To accelerate even a relatively small spacecraft, say 1,000 tons, to 10% of light speed, you would need energy on the order of the total annual energy output of the entire planet Earth, and that is just for acceleration. You also need to slow down when you arrive, which requires roughly the same amount of energy again. More realistically, for a large spacecraft capable of sustaining a human community, we might achieve 1 to 2% of light speed. At 1% of light speed, the journey to Proxima Centauri takes 424 years. At 2%, roughly 212 years. And remember, Proxima Centauri is the nearest star. For more distant targets, the travel times explode. TRAPPIST-1 at 1% light speed. 3,900 years. That is longer than the entirety of recorded human history. Think about that. When the ship launched, the Roman Empire had not yet fallen. By the time it arrives, the entire history of Western civilization, and then some, would have elapsed. Now you see the problem. Now you understand why the generation ship concept exists. It is not because anyone wants to build one. It is because, given the laws of physics as we understand them, and the limitations of any foreseeable propulsion technology, a generation ship might be the only way to physically transport living human beings to another star system. It is the option of last resort, the option you turn to when you have exhausted every other possibility and still need to cross an ocean of emptiness that is simply too vast for any single human lifetime. A generation ship, in its most basic definition, is a spacecraft designed to travel interstellar distances at sublight speeds over a period so long that multiple generations of human beings would live and die on board during the journey. The people who launch the ship are not the people who arrive. Their children are not the people who arrive. Their grandchildren are not the people who arrive. Potentially dozens or even hundreds of generations would be born, live their entire lives, and die within the ship before the final generation, the arrival generation, reaches the destination and steps off the ship onto a new world. It is a concept that is simultaneously awe-inspiring in its ambition and deeply troubling in its implications, and the more you examine it, the more troubling it becomes. The idea of a generation ship is not new. It has been floating around in human thought for over a century. One of the earliest conceptualizations came from Robert Goddard, the man often called the father of modern rocketry. In 1918, Goddard wrote an essay called The Last Migration, in which he described the idea of an interstellar arc that would carry human beings to other star systems over very long periods. Goddard was so uncertain about the reception of this idea that he sealed the essay, and it was not published during his lifetime. He knew it would sound like science fiction. He knew people would think he was crazy. But the seed was planted. In 1929, the physicist J.D. Bernal published a book called The World, the Flesh and the Devil, in which he proposed what became known as the Bernal Sphere, a hollow spherical space habitat roughly 16 kilometers in diameter that could house 20 to 30,000 people. Bernal envisioned these spheres as self-sustaining worlds that could potentially travel between stars. Around the same time, other thinkers were developing similar ideas. The concept was in the air. Humanity was beginning to think seriously about what interstellar travel would actually entail, and the horrifying realization was setting in that it would entail far more than anyone had imagined. But it was in the world of science fiction that the generation ship concept truly came alive. and it was through fiction that some of the most profound problems with the concept were first identified. In 1941, Robert Heinlein published a novella called Universe, later expanded and published together with its sequel as Orphans of the Sky. In this story, Heinlein imagines a generation ship whose inhabitants have completely forgotten that they are on a ship. Over the centuries, knowledge has been lost, society has regressed, and the people living inside the vessel believe that the ship is the universe. The concept of outside, the concept of stars, the concept of a destination, all of these have been lost. They are myths. Legends. Heresies. The people who maintain the engines do so as a religious ritual, not as a technical necessity they understand. This was fiction, but it was prescient fiction. Because the sociological and psychological problems Heinlein identified, the forgetting, the cultural regression, the loss of purpose, these are problems that modern scientists take very seriously when discussing generation ships. Since Heinlein, hundreds of authors, filmmakers, and game designers have explored the generation ship concept. Brian Aldiss in Non-Stop, Arthur C. Clarke in Rendezvous with Rama, the films Pandorum, Passengers, Wall-E television, shows like The 100, Avenue 5, aspects of The Expanse, video games like Mass Effect, Stellaris, FTL. Each of these works explores different facets of the generation ship concept, and each of them, whether intentionally or not, reveals another layer of horror beneath the beautiful surface. But we are not here today to talk about fiction. We are here to talk about reality. We are here to talk about what would actually happen if humanity attempted to build and operate a generation ship. And I want to be clear about something from the outset. The challenges are not just difficult. They are not just hard engineering problems that we will solve eventually. Some of these challenges strike at the very core of what it means to be human. They raise questions about freedom, consent, identity, purpose, and morality that do not have clean answers. So let us start with the engineering, because that is the part most people think about first, and then we will gradually move into the territory that keeps scientists awake at night. The first question is obvious. How big does a generation ship need to be? And the answer depends on one critical factor. How many people do you need to put on it? This might seem like a simple question, but it is not. It is a question of genetics, and the answer has been debated by population geneticists for decades. The issue is genetic diversity. When a small population is isolated from the larger human gene pool, a phenomenon called genetic drift occurs. Random variations in which genes get passed to the next generation become amplified. Rare alleles can be lost entirely. Harmful recessive traits can become more common. Over many generations, this leads to inbreeding depression, a reduction in biological fitness characterized by increased susceptibility to disease, reduced fertility, and a higher incidence of genetic disorders. You have seen this in the real world. Royal families throughout history who married within a small pool of relatives. Island populations that developed distinctive and sometimes harmful genetic characteristics. Dog breeds that have been overbred to the point of chronic health problems. On a generation ship, this process would be happening over centuries, and there is no external gene pool to introduce fresh genetic material. So what is the minimum number of people you need? The answer varies depending on who you ask and what assumptions they make. A study from Portland State University in 2018 suggested that with very careful genetic management, as few as 98 people could maintain sufficient genetic diversity over multiple generations. But this number comes with enormous caveats. It assumes perfect genetic screening. It assumes that reproduction is carefully controlled and managed by some authority. It assumes no catastrophic events that reduce the population. It assumes compliance from every single individual over every single generation. In other words, it assumes a level of control over human reproduction that is not only technically demanding, but ethically nightmarish, which we will discuss later. Most geneticists and anthropologists who study this question suggest much higher numbers. A frequently cited figure is 10,000 people as a minimum viable population for a multi-generational space journey. Some researchers push this number even higher, to 40,000 or 50,000, to provide a truly robust buffer against genetic drift, epidemics, and catastrophic population losses. Let us split the difference and say that a reasonable generation ship would carry between 10,000 and 50,000 people. Now think about what that means. That is a small city. You need to put a small city inside a spacecraft and keep it running for centuries. How much space does a city need? Well, on Earth, population density varies enormously. Manhattan has a population density of about 27,000 people per square kilometre. But Manhattan is not self-sustaining. It imports all of its food, water and energy from outside. A generation ship cannot import anything. Everything must be produced internally. So you need not only living space, but agricultural space, industrial space, recreational space, storage space, infrastructure space, and vast amounts of space for the systems that keep everyone alive. Life support, power generation, waste processing, water treatment, atmospheric management, and more. Let us think about just the agricultural component. On Earth, it takes roughly 1,500 to 2,000 square meters of agricultural land to feed one person for a year using traditional farming methods. For 10,000 people, that is 15 to 20 square kilometers of farmland. Now, on a generation ship, you would not use traditional farming. You would use advanced techniques like hydroponics, growing plants in nutrient-rich water instead of soil, aeroponics, growing plants with their roots suspended in a nutrient mist, and vertical farming, stacking growing layers on top of each other. These techniques can dramatically reduce the space needed, perhaps by a factor of 10 or even more. But even with a 10-fold reduction, you still need 1.5 to 2 square kilometers of dedicated growing space for 10,000 people. And that is just for plant-based food. If you want to include any form of animal protein, whether from actual livestock, fish farming, insect farming, or cultured meat production, you need additional space and resources. Then there is living space. On the International Space Station, astronauts have roughly 100 cubic meters of habitable volume each. And they are there for months, not lifetimes. For people who will spend their entire lives on the ship, you need dramatically more space per person. Studies on psychological well-being in confined environments suggest that a minimum of 50 to 100 square meters of personal living space per person is needed to prevent serious psychological deterioration over long periods. For 10,000 people, that is 500,000 to 1 million square meters of living space alone. And then there is communal space, recreational space, educational facilities, medical facilities, industrial areas, corridors, maintenance spaces, and all the infrastructure that makes a society function. Parks, meeting halls, sports facilities, cultural venues. You need all of it, because without it, the psychological pressure of confinement will crush the inhabitants. When you add it all up, serious engineering proposals for generation ships tend to converge on truly staggering dimensions. For a ship carrying 10,000 people, you are looking at a structure roughly 8 to 20 kilometers long and 2 to 5 kilometers in diameter. For 50,000 people, 20 to 32 kilometers long and 5 to 8 kilometers in diameter. To put that in perspective, the International Space Station, the largest structure humanity has ever built in space, is approximately 109 meters long and 73 meters wide. It has a mass of about 420 metric tons. A generation ship for 10,000 people would need to be roughly 100 times longer and 30 times wider than the ISS, with a mass measured not in hundreds of tons but in billions of tons. This would be, by an almost incomprehensible margin, the largest, most complex, most expensive structure ever built by human beings. The total cost of the International Space Station, including all launches and assembly, is roughly $150 billion. A generation ship would likely cost thousands of times more. We are talking about an investment that would dwarf the GDP of every nation on Earth combined. and you cannot build it on Earth and launch it. The mass is far too great. No rocket, no launch system, nothing we can conceive of could lift billions of tons off the surface of the Earth against the pull of gravity. A generation ship would have to be built in space. And that means you need an entire space-based industrial infrastructure first. Mining operations on asteroids and moons to extract raw materials, smelting and manufacturing facilities in orbit, construction yards in microgravity. A workforce of thousands, possibly tens of thousands, living and working in space for decades during the construction phase. You need to build the tools to build the ship. The scale of the endeavour is almost beyond comprehension, but let us assume, for the sake of argument, that we solve the construction problem. Let us assume that a century or two from now, humanity has a robust space-based industrial economy, that we are mining asteroids and building large structures in space as a matter of routine. Even then, the engineering challenges of the ship itself are monumental. Let us start with one of the most fundamental: gravity. Human beings evolved on a planet with a gravitational pull of 1g, roughly 9.8 meters per second squared. Our entire biology is designed for this gravitational environment. Our bones are structured to support our weight under 1g. Our muscles are sized and shaped for 1g. Our cardiovascular system is calibrated to pump blood against 1g. Our vestibular system, the part of our inner ear that governs balance and spatial orientation, is tuned to 1g. Take away gravity, and terrible things happen. In zero gravity, astronauts lose bone density at a rate of roughly 1 to 2% per month. Their muscles atrophy rapidly. Their cardiovascular system weakens because the heart does not have to work as hard. Fluid redistributes upward, causing facial puffiness, increased intracranial pressure, and vision problems. The immune system becomes compromised. Even with rigorous exercise regimes, astronauts on the ISS experience significant physiological deterioration during missions of 6 months to a year. Now imagine not 6 months, but an entire lifetime. Multiple lifetimes. Generations of human beings born and raised in zero gravity would be fundamentally, perhaps irreversibly, changed. Their bones would be thin and fragile. Their muscles would be weak. Their hearts would be small and inefficient. If they ever arrived at a planet with Earth-like gravity, they might not be able to stand up. They might not survive. So a generation ship needs artificial gravity, and the only known way to create artificial gravity without exotic physics is rotation. If you spin a spacecraft, the centrifugal force experienced by objects on the inner surface of the rotating structure mimics gravitational pull. The faster you spin, and the larger the radius, the stronger the apparent gravity. This is well understood physics. It is how those spinning carnival rides work, the ones that pin you against the wall. The same principle, scaled up enormously, can create a livable gravitational environment inside a spacecraft. But it is not as simple as just spinning the ship. There are significant complications. First, the rotation rate. If the ship spins too fast, the Coriolis effect becomes overwhelming. The Coriolis effect is an apparent force that acts on objects moving within a rotating reference frame. In practical terms, it means that if you are standing inside a spinning habitat and you drop a ball, it does not fall straight down. It curves. If you throw a ball across a room, it curves. If you pour water from a pitcher, the stream curves. If you walk in a straight line, you feel a subtle push to one side. At high rotation rates, these effects become severe enough to cause persistent motion sickness, disorientation, and difficulty performing basic tasks. Studies suggest that for most people, rotation rates above about 2 revolutions per minute cause significant discomfort. To keep the rotation rate below 2 rpm while maintaining 1g of apparent gravity, you need a radius of at least 224 meters. That means the rotating section of the ship needs to be at least 448 meters in diameter, and that is the minimum. For genuine comfort, For a living environment where the Coriolis effect is barely noticeable, you want a much larger radius. 1 kilometer or more. Second, the gravity gradient. In a rotating habitat, the apparent gravity depends on your distance from the axis of rotation. On the inner surface, at the full radius, you get the maximum gravity, but as you move toward the axis, gravity decreases. At the exact center of the rotating structure, the axis, there is zero gravity. This means that a multi-story building inside the habitat would have slightly different gravity on each floor. The difference in gravity between your feet and your head is called the gravity gradient, and if the radius is too small, this gradient can be perceptible and uncomfortable. Your feet might experience 1 g while your head experiences 0.97 g. This does not sound like much, but over a lifetime, it could have physiological and psychological effects. Third, the structural engineering. A structure kilometers in diameter, rotating once or twice per minute, is under enormous centrifugal stress. The materials need to be extraordinarily strong and lightweight. Current materials like steel and aluminum are not up to the task at this scale. You would likely need advanced composites, carbon nanotubes, or materials we have not yet invented. Several specific designs have been proposed over the decades. The O'Neill cylinder, conceived by physicist Gerard O'Neill in the 1970s, consists of 2 counter-rotating cylinders, each roughly 8 kilometers in diameter and 32 kilometers long. The interior surface is divided into alternating strips of land and windows, and the rotation provides 1 g of gravity on the land strips. The counter-rotation of the 2 cylinders cancels out gyroscopic effects that would otherwise make the structure difficult to steer. O'Neill designed these as space habitats orbiting in our own solar system, but the concept can be adapted for a generation ship by enclosing the structure, adding propulsion, and replacing the windows with artificial lighting. The Stanford Taurus, designed during a 1975 NASA summer study, is a donut-shaped rotating habitat, roughly 1.8 kilometers in diameter. The interior of the Taurus tube, where people live, is roughly 130 meters across. The Taurus rotates at about 1 revolution per minute, producing nearly 1 g on the outer rim. The original design housed about 10,000 people. It is a more compact and structurally efficient design than the O'Neill cylinder, but it provides less total habitable area. The Bernal sphere is a spherical habitat, roughly 500 meters in radius, rotating to provide gravity. People live on the inner equatorial surface, where the centrifugal force is greatest. The poles of the sphere are low gravity or zero gravity zones. The original proposal by J.D. Bernal envisioned a sphere 16 kilometers in diameter housing 20 to 30,000 people, though smaller versions are more commonly discussed. Each of these designs has strengths and weaknesses, and a real generation ship would likely incorporate elements of multiple designs. But they all share a common requirement: they must be enormously large, incredibly strong, and built with a precision and reliability that far exceeds anything humanity has ever achieved in engineering. Because this structure must work perfectly, or nearly perfectly, for centuries. There is no repair dock. There is no resupply mission. There is no rescue. If the structural integrity of the rotating habitat fails, if the bearings that allow it to spin give out, if a meteorite punctures the hull, the consequences range from severe to catastrophic. And we have never built anything that works without maintenance or repair for even a fraction of that time. Let us talk about what keeps everyone alive. Life support. On Earth, we take for granted the systems that sustain us. The atmosphere provides breathable air. The water cycle provides drinkable water. Ecosystems produce food. Decomposition recycles nutrients. The ozone layer blocks radiation. The magnetosphere deflects solar wind. These systems have been running with occasional hiccups for billions of years. They involve trillions upon trillions of organisms in an interconnected web of staggering complexity that we still do not fully understand. A generation ship must replicate these systems in a tiny fraction of the space, with absolute reliability, for centuries with no external inputs whatsoever. Let us start with air. Human beings need to breathe an atmosphere that is roughly 21% oxygen and 78% nitrogen, with trace amounts of other gases at a pressure of about 1 atmosphere, around 101 kilopascals. Too little oxygen and people suffocate. Too much oxygen and fires become uncontrollable, and oxygen toxicity damages the lungs. Too much carbon dioxide, and people experience headaches, confusion, and eventually death. The atmosphere must be maintained within very narrow parameters, constantly, for the entire duration of the journey. On the ISS, air management is achieved through a combination of methods. Oxygen is generated primarily through electrolysis, using electricity to split water into hydrogen and oxygen. Carbon dioxide is removed using chemical scrubbers, but the ISS receives regular resupply missions. Filters are replaced, chemicals are replenished, equipment is repaired or replaced. A generation ship has none of these luxuries. Everything must be recycled or regenerated internally. The most promising approach for long-term atmospheric management on a generation ship is bioregenerative life support. This means using living organisms, primarily plants, algae, and cyanobacteria, to convert carbon dioxide back into oxygen through photosynthesis, just as they do on Earth. A sufficiently large and diverse plant ecosystem could theoretically maintain atmospheric balance indefinitely, as it does on our planet. But the key word is sufficiently large and diverse. The Earth's biosphere contains an estimated 8.7 million species of organisms, all interacting in complex food webs and nutrient cycles. A generation ship cannot replicate this. It must distill the essential functions of an entire planetary biosphere into a manageable, maintainable system. This is a challenge of extraordinary difficulty, and the field of bioregenerative life support systems, while it has made progress, is still in its infancy. We have not yet demonstrated the ability to maintain a closed-loop atmospheric system for more than a few years, let alone centuries. The Biosphere 2 experiment in the early 1990s is the closest thing we have to a test of this concept, and the results were not encouraging. Biosphere 2 was a 3.14-acre enclosed ecological system in Arizona, designed to be completely sealed and self-sustaining. It contained multiple biomes including a rainforest, an ocean, a desert, and agricultural areas. 8 people were sealed inside for 2 years. It did not go well. Oxygen levels dropped precipitously, falling from 21% to 14%, equivalent to an altitude of about 4,300 meters. Carbon dioxide levels fluctuated wildly. Many of the animal species died. Insect populations exploded in some areas and collapsed in others. Food production was insufficient, and the crew lost significant weight. Interpersonal conflicts became severe. The experiment did not achieve its goal of demonstrating a self-sustaining closed ecological system. Now, Biosphere 2 was a first attempt, and much was learned from it, but the fact remains that we have never successfully maintained a closed ecological system for more than a few years. A generation ship needs one to function for centuries. Water is equally critical. The human body is roughly 60% water. We need to drink about 2 liters per day, and we use vastly more for hygiene, cooking, agriculture, and industrial processes. On a generation ship, every single molecule of water must be recycled. Drinking water, wash water, agricultural runoff, humidity from the air, sweat, urine, even the water content of human waste. All of it must be collected, purified, and recirculated. The ISS currently achieves water recycling efficiency of about 90%. That sounds impressive, but it means they lose 10% of their water with each cycle, and that 10% must be resupplied from Earth. A generation ship needs to achieve water recycling efficiency of 99.9% or higher, because there are no resupply missions. Losing even a tiny fraction of water with each cycle means that over centuries, the ship slowly dries out. Advanced filtration systems, biological water treatment using constructed wetlands, UV purification, reverse osmosis, distillation. All of these would need to be combined into a comprehensive water management system of extraordinary reliability and efficiency. And then there is food. This is perhaps the most challenging aspect of life support, because food production requires enormous resources of space, water, energy, and labour, and because the failure of food production is a death sentence for the entire ship. On Earth, feeding 10,000 people requires a vast agricultural enterprise. On a generation ship, this enterprise must function in an enclosed, artificial environment with no sunlight, limited soil or no oil at all, limited water, and limited space. The most promising approaches involve a combination of technologies: hydroponics, growing plants with their roots in nutrient-rich water rather than soil, can produce dramatically higher yields per unit area than traditional agriculture. Some hydroponic systems can produce 10 to 20 times more food per square meter than conventional farming. Aeroponics, where plant roots are suspended in air and periodically misted with nutrient solution, is even more efficient in terms of water usage, using up to 90% less water than traditional irrigation. Vertical farming, stacking multiple growing layers on top of each other, further multiplies the effective growing area within a given volume. These technologies are being developed and deployed on Earth right now, and they show enormous promise. But scaling them up to feed 10,000 people or more continuously for centuries in a sealed spacecraft is a challenge of a completely different order. Dietary variety is another concern. Human beings do not do well on monotonous diets, either nutritionally or psychologically. A generation ship would need to produce a wide range of fruits, vegetables, grains, and protein sources. Some of this could come from plant-based sources: legumes, soy, various grains, and vegetables can provide complete nutrition. But many people find an entirely plant-based diet psychologically unsatisfying, especially over a lifetime with no alternative. Aquaponics, combining fish farming with plant cultivation in a symbiotic system, could provide both protein and plant foods. Insect farming, particularly crickets and mealworms, is an extraordinarily efficient way to produce protein, requiring a fraction of the water, feed, and space that conventional livestock requires. Cultured meat, grown from animal cells in a laboratory without raising and slaughtering animals, could provide familiar meat products without the enormous resource cost of traditional animal husbandry. Each of these food production methods has its own requirements in terms of space, energy, water, labor, and technology, and all of them must function reliably for the duration of the journey. Here is a terrifying thought about food production on a generation ship. Consider what happens if a plant disease strikes. On Earth, crop diseases can be devastating. The Irish potato famine of the 1840s killed roughly 1 million people and drove another million to emigrate, and that was in a country that had access to the rest of the world for help. On a generation ship, there is no outside help. If a pathogen infects the primary food crop, if a pest population explodes out of control, if a critical component of the agricultural system fails, the result could be famine. And famine on a generation ship does not mean hardship and suffering. It means the potential end of the entire mission. The entire species' hope for interstellar colonization gone because of a fungus or an insect. This is why agricultural biodiversity on a generation ship is critical. You cannot put all your eggs in one basket. You need multiple food production systems using multiple crop varieties with multiple redundant backup systems. But redundancy requires space and resources, which are precisely the things a generation ship has in limited supply. Now let us talk about energy. Everything on the ship, the life support systems, the agricultural lighting, the atmospheric management, the water recycling, the computers, the communications, the propulsion, the manufacturing, the heating, everything runs on energy. And in the vast emptiness between stars, there is essentially no external energy to harvest. Solar panels, which work beautifully in Earth orbit where the sun provides about 1,360 watts per square meter, become useless once you are far from any star. In the interstellar void, the ambient light level is essentially zero. You must carry your own power source, and it must generate enormous amounts of power reliably for centuries. The most promising candidate for generation ship power is nuclear energy, either fission or fusion. Nuclear fission, the splitting of heavy atoms like uranium or thorium, is a proven technology. We have been running fission reactors on Earth since the 1950s. We know how to build them, how to operate them, and how to maintain them. A fission reactor can generate enormous amounts of power from a relatively small amount of fuel. However, fission reactors produce radioactive waste, which on a generation ship would need to be carefully stored and managed. They also require a supply of fissile material, which, while it lasts a long time, is not infinite. Over centuries of operation, the fuel would need to be replenished or recycled, potentially using breeder reactor technology that creates new fissile material from non-fissile precursors as part of the reaction cycle. Nuclear fusion, the combining of light atoms like hydrogen isotopes into heavier atoms, is the holy grail of energy production. It is the process that powers the sun and all other stars. Fusion produces vastly more energy per unit of fuel than fission. It produces minimal radioactive waste. And its fuel, particularly deuterium, a heavy isotope of hydrogen, is abundant in water and could potentially be carried in enormous quantities. The problem is that we have not yet achieved sustained controlled nuclear fusion on Earth. As of my knowledge, we have made significant progress, and experimental fusion reactors like ITER and various private ventures have made strides. But we are not yet at the point where fusion is a reliable, commercially viable energy source. A generation ship built in the next century or two would most likely need to rely on advanced fission reactors, with fusion as a potential upgrade if the technology matures. Antimatter is sometimes proposed as a power source, and it is in theory the most energy-dense fuel possible. When matter meets antimatter, they annihilate each other, and 100% of their combined mass is converted to energy, according to Einstein's famous equation E equals mc squared. 1 gram of antimatter reacting with 1 gram of matter releases approximately 180 trillion joules of energy, equivalent to about 43 kilotons of TNT, nearly 3 times the energy of the Hiroshima bomb. The problem is that we can currently produce only nanograms of antimatter per year at a cost of roughly $62.5 trillion per gram. And storing antimatter is extraordinarily dangerous, because it annihilates on contact with any normal matter, meaning it must be suspended in a perfect vacuum using electromagnetic fields. Antimatter propulsion and power generation remain firmly in the realm of theoretical possibility rather than practical engineering. Whatever the power source, a generation ship would need multiple redundant power systems. If the primary reactor fails, a backup must take over instantly and seamlessly. If the backup fails, a third system must be ready. The consequences of a total power failure on a generation ship are immediate and absolute. Without power, the atmospheric systems stop. Carbon dioxide builds up. Oxygen depletes. Temperature drops or soars, depending on the ship's position and design. The agricultural lights go dark. The food supply begins to die. Water stops being recycled. Within hours, the ship begins to die. Within days, the people begin to die. Triple or quadruple redundancy in power systems is not a luxury. It is a bare minimum requirement for survival. And now we come to something that many people do not think about when they imagine generation ships, but which is one of the most persistent and dangerous threats to everyone on board. Radiation. Space is an incredibly hostile radiation environment, and the interstellar medium is worse than near-Earth space in many ways. On the surface of the Earth, we are protected from the worst of space radiation by 2 mechanisms. The first is Earth's magnetosphere, a magnetic field generated by the planet's liquid iron core that deflects charged particles, particularly those in the solar wind. The second is the atmosphere, which absorbs and scatters high-energy particles and electromagnetic radiation. In space, you have neither of these protections. And on a generation ship traveling through interstellar space, the radiation environment is dominated by galactic cosmic rays. Galactic cosmic rays are high-energy particles, primarily protons but also heavier nuclei, that originate from outside our solar system, likely from supernova remnants and other energetic astrophysical sources. They travel at nearly the speed of light and carry enormous energy. When a galactic cosmic ray strikes a material surface, like the hull of a spacecraft, it does not just stop. It creates a cascade of secondary particles, neutrons, pions, muons, gamma rays, that shower into the structure behind the hull. These secondary particles can be even more biologically damaging than the primary cosmic ray. Shielding against galactic cosmic rays is extraordinarily difficult because of their extreme energy. Unlike solar particle events, which consist of lower energy particles that can be blocked by relatively thin shielding, galactic cosmic rays require enormous amounts of material to attenuate. The health effects of chronic radiation exposure are severe and cumulative. Increased cancer risk is the most well-known consequence, but it is far from the only one. Chronic radiation exposure damages the central nervous system, potentially leading to cognitive decline, memory loss, and reduced motor function. It causes cataracts. It damages the cardiovascular system. It accelerates aging. And crucially for a generation ship, it damages reproductive cells and developing embryos. Radiation-induced mutations in sperm and egg cells can lead to birth defects, genetic disorders, and reduced fertility. Over multiple generations, the accumulated genetic damage from chronic radiation exposure could be devastating, leading to a progressive deterioration of the population's health and genetic integrity. How do you protect against this? There are several approaches, none of them perfect. Passive shielding involves placing thick layers of material between the radiation and the crew. Hydrogen-rich materials are most effective at stopping galactic cosmic rays, because hydrogen nuclei, being roughly the same mass as the incoming protons, absorb the most energy per collision. Water, polyethylene, and liquid hydrogen are all effective shielding materials, but the amount needed is enormous. Effective passive shielding against galactic cosmic rays might require several meters of water or equivalent material surrounding the entire habitable volume of the ship. For a ship with a habitable volume of millions of cubic meters, the mass of shielding alone could be millions or billions of tons, potentially doubling or tripling the total mass of the ship. This creates a cascading engineering nightmare. More mass means more structural support needed, more propulsion needed, more fuel needed, which means more mass, which means more structural support, and so on. Active shielding is an alternative that does not add as much mass. The idea is to create an artificial magnetic field around the ship, analogous to Earth's magnetosphere, that deflects charged particles before they reach the hull. This is technically feasible in principle. We know how to generate powerful magnetic fields. But the engineering challenges are formidable. You need superconducting magnets of enormous size, powered continuously for centuries, generating a field strong enough and large enough to deflect galactic cosmic rays with energies of billions of electron volts. The field would need to extend many kilometers from the ship to be effective, and it would need to be maintained without interruption, because even a brief failure would expose the crew to full, unshielded cosmic ray bombardment. Some proposals combine passive and active shielding, using a magnetic field to deflect most particles and a thinner layer of passive shielding to catch the rest. This is probably the most realistic approach, but it adds complexity, mass, and potential failure modes to an already impossibly complex system. There is another radiation-related concern that is rarely discussed, but extremely important. Pharmaceutical protection. On Earth, cancer treatments include radiation therapy, chemotherapy, and increasingly targeted molecular therapies. On a generation ship, the medical system would need to be able to treat radiation-induced cancers and other radiation damage, potentially at rates much higher than on Earth, using only the resources available on the ship. This means onboard pharmaceutical manufacturing, medical imaging equipment, surgical facilities, and trained medical personnel, all maintained and replenished over centuries with no external supply. A single generation of inadequate medical care could allow a wave of untreated cancers and genetic disorders to sweep through the population, reducing the workforce, increasing the burden on remaining healthy individuals, and potentially triggering a cascading social and biological crisis. There is yet another threat from the interstellar environment that most people do not consider: the interstellar medium itself. Space between stars is not perfectly empty. It contains extremely sparse gas and dust, roughly 1 atom per cubic centimetre on average, though the density varies. At everyday speeds, this is negligible. But a generation ship travelling at even 1% of the speed of light is moving at 3,000 kilometers per second. At that speed, the interstellar medium becomes a significant hazard. Individual atoms and molecules striking the ship at relativistic speeds carry enormous kinetic energy. A single proton hitting the ship at 1% of the speed of light has about the same energy as a fast baseball. And the ship is hitting billions of these per second across its forward cross-section. Over time, this constitutes an erosive bombardment that can damage the hull. It also contributes to the radiation environment inside the ship, as these high-speed impacts generate secondary radiation. Even more concerning is the possibility of encountering larger particles, dust grains, tiny pebbles, or larger debris. The interstellar medium contains dust grains ranging in size from fractions of a micrometer to potentially larger objects. A grain of sand, massing perhaps 1 milligram, striking the ship at 1% of the speed of light, would impact with an energy of roughly 45 million joules. That is comparable to several kilograms of TNT. A grain of sand, a pebble weighing 1 gram, would hit with the energy of a small bomb. And detecting such tiny objects at the distances required to take evasive action millions of kilometers ahead of the ship is a technological challenge that borders on the impossible. The standard proposed solution is a combination of shielding and active defense. The forward section of the ship would be heavily armored, potentially with a Whipple shield, a multi-layer shield where the outer layer vaporizes incoming particles and the inner layers absorb the expanding debris cloud. Some proposals include active defense systems using lasers or particle beams to detect and vaporize larger debris ahead of the ship. Others propose a forward-mounted magnetic field to deflect charged particles and a physical plow or leading structure to absorb impacts. None of these solutions are without cost in terms of mass, energy, and complexity. Now let us talk about the engine. The propulsion system. Because none of these challenges matter if you cannot actually move the ship, and moving a structure massing billions of tons to interstellar velocities is perhaps the single greatest engineering challenge of the entire project. The fundamental constraint is the Tsiolkovsky rocket equation, one of the most elegant and most merciless equations in all of engineering. The equation describes the relationship between a rocket's final velocity, the exhaust velocity of its propellant, and the ratio of its initial mass plus to its final mass. In simple terms, it says this: to go faster, you need more fuel. But more fuel means more mass, which means you need even more fuel to push that fuel. The relationship is exponential, meaning that the fuel requirement grows dramatically with each increment of desired speed. For conventional chemical rockets, the exhaust velocity is relatively low, about 4 to 5 kilometers per second for the best engines. To accelerate a payload to 1% of light speed, 3,000 kilometers per second with a chemical rocket. The mass ratio, the ratio of fuel to payload, would need to be approximately e to the power of 600. That is a number so large it is effectively infinite. Chemical rockets are completely, utterly, laughably useless for interstellar travel. This is why every serious interstellar propulsion proposal involves either nuclear energy or even more exotic power sources. Let me walk through the main candidates. Nuclear pulse propulsion, the concept behind Project Orion, is one of the oldest and in some ways most audacious proposals. The idea is simple, even if the execution is terrifying. You detonate nuclear bombs behind the ship and ride the shockwave. Each detonation pushes a massive pusher plate at the rear of the ship, accelerating the entire vehicle. Project Orion was a real research program funded by the US government from 1958 to 1965, with physicist Freeman Dyson as one of its key participants. The team calculated that with 1960s technology, a nuclear pulse ship could reach speeds of 3 to 5% of the speed of light. The Super Orion concept, a ship massing approximately 8 million tons, could potentially carry a small city and reach even higher speeds. The project was killed not by engineering limitations, but by politics. Specifically the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. But the physics works. Dyson himself was quoted as saying that with Project Orion, we could have explored the entire solar system and begun interstellar missions with the technology available in the 1960s. Whether he was right is debatable, but the fact that this concept received serious study from serious scientists for nearly a decade speaks to its theoretical viability. Nuclear fusion propulsion is the basis of Project Daedalus, a detailed study conducted by the British Interplanetary Society from 1973 to 1978. Daedalus was designed as an unmanned probe, not a generation ship, but the propulsion concept is applicable. The Daedalus probe would use pellets of deuterium and helium-3 ignited by electron beam ignition in an inertial confinement fusion drive. The exhaust velocity would be approximately 10,000 kilometers per second, enormously higher than chemical rockets. Daedalus was calculated to reach 12% of the speed of light, fast enough to reach Barnard's star in about 50 years. The probe itself would mass 54,000 tons, of which 50,000 was fuel. Project Icarus, a successor study conducted from 2009 to 2014, updated the Daedalus concept with modern technology and explored additional design options. Both studies concluded that fusion propulsion is theoretically feasible for interstellar travel, but practical fusion drives are dependent on our ability to achieve controlled nuclear fusion, which remains elusive. Antimatter propulsion represents the theoretical upper limit of propulsion efficiency. Matter-antimatter annihilation converts 100% of the fuel mass to energy, compared to about 0.7% for nuclear fission and about 0.4% for nuclear fusion. An antimatter drive could theoretically achieve exhaust velocities close to the speed of light, enabling truly rapid interstellar travel. But as I mentioned earlier, the practical barriers are immense. We can produce only infinitesimal amounts of antimatter, we cannot store it safely in large quantities, and the cost is astronomical. Antimatter propulsion is a technology for the far future, if it is achievable at all. Laser-pushed sails, the concept behind Breakthrough Starshot, offer a fundamentally different approach. Instead of carrying fuel, the spacecraft is pushed by a powerful laser beam aimed at a large, lightweight reflective sail. The laser array remains behind, in the home star system, and the spacecraft carries no fuel at all. This elegantly sidesteps the tyranny of the rocket equation, because the propulsion mass, the Yaser, and its power source stays at home and does not need to be accelerated with the ship. Breakthrough Starshot proposes using a 100 gigawatt laser array to accelerate a gram-scale probe to 20% of the speed of light, reaching Alpha Centauri in about 20 years. The concept is feasible for tiny lightweight probes, but scaling it up to a generation ship massing billions of tons would require a laser array of almost inconceivable power and size, potentially a continent-spanning structure producing petawatts of power. And there is the deceleration problem. The laser can push the sail to accelerate, but once the ship is far from the laser, there is no way to slow down. Some proposals suggest using a magnetic sail, or magsail, to brake against the interstellar medium or the destination star's stellar wind. But this technology is entirely theoretical. The Bussard ramjet, conceived by physicist Robert Bussard in 1960, is one of the most elegant interstellar propulsion concepts ever proposed. The idea is to use a giant magnetic scoop, potentially hundreds or thousands of kilometers in diameter, to collect hydrogen from the interstellar medium and use it as fuel for a fusion reactor. The ship would essentially refuel itself as it travels, potentially enabling indefinite acceleration and very high speeds. It is a beautiful concept. Unfortunately, subsequent analysis has revealed serious problems. The interstellar medium is extremely sparse, and the drag created by the magnetic scoop collecting hydrogen may exceed the thrust generated by fusing that hydrogen. The ramjet, it appears, may actually slow down rather than speed up. Modifications to the concept have been proposed, such as using the scoop only for deceleration, but the original vision of a ramjet that accelerates indefinitely appears to be unworkable with known physics. Realistically, a generation ship would likely use a combination of propulsion methods. Perhaps a laser-pushed sail for initial acceleration, boosting the ship to a few % of light speed as it leaves the home star system. Then an onboard fusion or fission drive for mid-course corrections and course maintenance. And finally, a magsail or reverse thrust for deceleration as it approaches the destination. This multi-stage approach combines the advantages of different technologies while mitigating their individual weaknesses, but it also combines their complexities and failure modes, and each transition between propulsion modes represents a critical moment where things can go wrong. I want to pause here for a moment, because we have been talking about engineering for quite a while now, and I want to make sure you appreciate the full scope of what we have covered. We have talked about the size of the ship, the structural design, the rotation for artificial gravity, the life support systems, air, water, food, waste management, the energy systems, the radiation shielding, the interstellar medium hazards, the propulsion. Each of these is, individually, one of the hardest engineering challenges humanity has ever faced. And a generation ship must solve all of them simultaneously in a single integrated system that works without major failure for centuries. There is nothing in human engineering history that comes remotely close to this level of complexity and required reliability. The most complex systems we have ever built, nuclear power plants, aircraft carriers, the IS, modern microprocessors, all of these require regular maintenance, periodic upgrades, and eventual replacement. A generation ship must be designed to be maintained and repaired using only the resources and skills available on board, with no external supply chain, for a period of time longer than most human civilizations have lasted. And here is the thing. Here is what makes the generation ship concept so uniquely terrifying. The engineering, as impossibly difficult as it is arguably the easy part, because the engineering challenges are at least theoretically solvable. They are physics problems and material science problems and industrial engineering problems. They are hard, but they are the kind of hard that human beings are good at solving. Given enough time, enough resources, enough ingenuity, we can probably figure out how to build the ship. The much harder problems, the problems that might truly be unsolvable, are the human problems. The biological, psychological, sociological, and ethical challenges that arise when you try to confine a community of human beings inside a metal structure for centuries with no way out. These are the problems that keep researchers up at night. These are the problems that might make generation ships not just difficult, but fundamentally impossible. And these are the problems we are going to talk about now. If you are still here, and I hope you are, then you are about to enter the most disturbing part of this discussion. And I want to remind you, if you are enjoying this deep dive, if this is the kind of content that feeds your curiosity, then please take a moment to hit that like button. It helps this video reach more people who are passionate about these topics. Subscribe to the channel if you have not already, because we do deep dives like this regularly. And leave a comment telling me which of the engineering challenges we just discussed surprised you the most. Was it the radiation? The food production? The Coriolis effect? I want to know what caught your attention. Alright, let us continue. Let us start with biology. Because before we get to the mind, before we get to society, before we get to ethics, we need to talk about what happens to the human body over the course of centuries in a sealed spacecraft. And the answer is, it changes, whether you want it to or not. The first biological challenge is the one we already mentioned in the context of ship design, the minimum viable population and genetic diversity. But I want to go deeper now, because the genetic implications are more profound than most people realize. When a small population is isolated, genetic drift, the random fluctuation of allele frequencies from one generation to the next, becomes a dominant force. In a large population, drift is negligible because the randomness averages out over millions of individuals. In a small population, it does not. An allele that is rare in the initial population can, purely by chance, become common or disappear entirely within a few generations. This is the founder effect. The genetic makeup of the founding population determines, to a large extent, the genetic makeup of all future generations. If the founders happen to carry a slightly higher frequency of a particular harmful recessive allele, that allele could become prevalent in the ship population within just a few generations, potentially causing widespread genetic disease. This has happened in real human populations. The Amish community in the United States descends from a small group of 18th century German immigrants. Due to the small founding population and subsequent social isolation, certain genetic disorders, particularly Ellis-Van Creveld syndrome and several forms of dwarfism, are far more common among the Amish than in the general population. The Ashkenazi Jewish population, which went through severe population bottlenecks, has elevated rates of certain genetic diseases, including Tay-Sachs disease, Gaucher's disease, and breast cancer, linked to BRCA gene mutations. These are real-world examples of what happens when a human population is small and isolated. On a generation ship, the population would be small and isolated for centuries, potentially dozens or hundreds of generations. The genetic consequences could be far more severe than anything we have seen in any human population on Earth. The standard proposed solution is genetic management, essentially controlling who reproduces with whom to maximize genetic diversity and minimize the expression of harmful traits. This could involve maintaining a database of everyone's genetic profile and using algorithms to recommend or mandate optimal breeding pairs. It could involve maintaining a frozen bank of sperm and egg cells collected from a large and genetically diverse population before launch, and using these to supplement the gene pool through artificial insemination or in vitro fertilization. It could involve screening embryos for genetic defects and selectively implanting only healthy ones. These are all technically feasible with current or near-future reproductive technology, but they raise enormous ethical questions that we will discuss shortly. For now, I will simply note that managing the genetics of a human population over centuries requires a level of reproductive control that has never been practiced in any human society, and that is profoundly at odds with concepts of individual freedom and bodily autonomy. But genetic drift and inbreeding are just the beginning of the biological story. There is a far stranger and more unsettling biological process that would be happening on the ship, one that cannot be controlled by any genetic management program. Evolution. Natural selection. The same process that has shaped every living thing on this planet for 4 billion years does not stop because you are on a spaceship. It keeps going, and on a generation ship, the evolutionary pressures are completely different from those on Earth. Consider what happens over many generations. The environment on the ship is different from the environment on Earth in numerous ways. The gravity might be slightly different. The air composition, even if carefully controlled, might be subtly different. The radiation environment is different. The diet is different. The activity patterns are different. The social environment is different. The pathogenic environment is different. Each of these differences creates different selective pressures, and over time, these pressures shape the population. Individuals who are slightly better adapted to life on the ship, whatever that means in this specific context, will tend to be healthier, to live longer, to have more children. Their genes will become more common in the population. Individuals who are slightly less well adapted will have fewer children. Their genes will become less common. Over dozens of generations, centuries of time, these subtle pressures add up. The people living on the ship might become slightly shorter if the ship's spaces favor shorter stature. They might develop different bone density, different muscle characteristics, different cardiovascular parameters. Their immune systems, without exposure to the vast diversity of pathogens found on Earth, might become weaker and more specialized, adapted to the specific microbial environment of the ship, but potentially helpless against novel pathogens they might encounter at the destination. Their visual system might adapt to the specific lighting conditions of the ship, which would almost certainly be different from natural sunlight. Their circadian rhythms might shift. Their psychology might change in subtle ways, with more introverted, more cooperative, more conformist individuals being selected for in the close confines of a small community where social conflict is extremely costly. This is not science fiction speculation. This is evolutionary biology. It is what would happen, given enough time. The people who arrive at the destination would not be the same biologically as the people who left. They would be a new population, adapted to life inside a metal tube, potentially poorly adapted to life on a planetary surface. They might struggle with the gravity of the new planet, even if it is similar to Earth's gravity. They might be overwhelmed by the microbial environment. They might be psychologically unprepared for open spaces, for weather, for the sheer overwhelming sensory experience of a natural world after a lifetime inside a controlled artificial environment. The arrival, which is supposed to be the triumphant culmination of centuries of sacrifice, might instead be a biological crisis. And there is an even more unsettling possibility. What if the evolution goes further? What if, over enough centuries, enough generations, the ship population diverges so far from baseline humanity that they are effectively a different subspecies? This might sound extreme, but consider anatomically modern humans and Neanderthals diverged in roughly 500,000 years. On a generation ship where the population is small, the environment is dramatically different, and the selective pressures are strong and consistent, evolutionary change could be accelerated. Perhaps not enough to create a new species in a few hundred years, but enough to create a population with noticeable physical and physiological differences from Earth humans. If faster-than-light communication with Earth is not possible, the two populations would diverge culturally as well. By the time the ship arrives at its destination, the colonists might be almost as alien to Earth humans as an extraterrestrial species would be. Let me talk about something even more immediate and practical. Pregnancy and childbirth on a generation ship. This is critically important, because the entire premise of a generation ship is that new generations will be born on board. Reproduction is not optional. It is the entire point. Without successful reproduction, the mission fails completely. And here is the disturbing truth. We know almost nothing about human reproduction in space. As of my knowledge, no human being has ever conceived, gestated, or been born in space. We have no data, zero, on how the space environment affects human pregnancy, fetal development, or childbirth. We do have some data from animal studies, and it is not particularly reassuring. Studies on rats and mice in microgravity and altered gravity environments have shown various effects on reproduction and development, including altered fetal development, changes in motor function and vestibular system development, and effects on bone and muscle development. But rats are not humans, and short-term animal studies in low Earth orbit are not the same as multi-generational human habitation in a rotating artificial gravity environment in deep interstellar space. We simply do not know what will happen. Every child born on the generation ship is an experiment. Every pregnancy is a voyage into the unknown. And the consequences of getting it wrong, of discovering that something about the ship environment is fundamentally incompatible with healthy human reproduction, would be catastrophic. If fertility rates drop too low, the population shrinks below viability. If birth defects increase, the genetic health of the population deteriorates. If infant mortality rises, The psychological impact on the community is devastating. The microbiome presents yet another biological challenge. The human body is not a single organism. It is an ecosystem. Every human being harbors trillions of microorganisms, bacteria, fungi, viruses, archaea, collectively known as the microbiome. These organisms are not passengers. They are essential partners. They help us digest food. They produce vitamins. They train our immune system. They influence our mood and cognitive function through the gut-brain axis. They protect us from harmful pathogens by occupying ecological niches and competing with invaders. The composition of the microbiome is influenced by environment, diet, social contact, and exposure to diverse microbial communities. On Earth, we are constantly exposed to new microorganisms from the soil, from water, from other people, from animals, from the environment. This constant influx maintains the diversity and resilience of our personal microbial ecosystem. On a generation ship, the microbial environment would be closed and limited. The same microorganisms would circulate among the same people in the same enclosed space for centuries. Without the constant influx of new microbial diversity, the ship's microbial ecosystem could become increasingly narrow and fragile. Certain species might go extinct within the ship, others might evolve and diversify in unexpected ways. The balance between beneficial and harmful microorganisms could shift. Antibiotic-resistant bacteria, always a concern, could become a nightmare in a closed system where resistant strains can spread through the entire population with no way to introduce fresh, sensitive strains to outcompete them. A pandemic of antibiotic-resistant bacteria on a generation ship could be an extinction event for the entire population. And then there is the question of medical care. On Earth, if you develop cancer, you go to an oncologist. If you need surgery, you go to a hospital with trained surgeons, advanced equipment, and a supply chain that provides everything from surgical gloves to chemotherapy drugs. On a generation ship, all of this must be provided internally. The ship must train its own doctors, manufacture its own drugs, build and maintain its own diagnostic equipment, and perform every medical procedure from routine checkups to emergency surgery using only the resources on board. This is an enormous challenge in itself, but it becomes even more daunting when you consider the timescale. Medical knowledge and techniques must be maintained and transmitted across generations. Medical equipment must be maintained or remanufactured as it wears out. Pharmaceutical production requires raw materials, laboratory facilities, and deep expertise in chemistry and biology. And the medical system must be able to handle not just routine ailments, but also the novel health challenges that arise from the unique environment of the ship. Challenges that no doctor on Earth has ever encountered or been trained for. We have now covered the biological challenges in considerable depth, but I saved the worst for last. Because the biological challenges, as daunting as they are, might still be solvable with enough technology and planning. The psychological challenges might not be. Let me paint a picture for you. Imagine that you are 20 years old. You live on a generation ship. Your great-great-great-grandparents boarded this ship 200 years ago. You have never seen Earth. Earth is a story to you, a collection of images and recordings in the ship's database. You know intellectually that your ancestors came from a planet with blue skies and green forests and vast oceans. You have seen the photographs, you have watched the videos, but you have never experienced any of it. You have never felt grass between your toes. You have never swum in a lake. You have never looked up at a sky that went on forever. Your entire world is the interior of this ship. The longest corridor on the ship is perhaps 2 kilometers. The largest open space is a park, a few hundred meters across, with carefully maintained trees and a small artificial pond. The sky above you is a curved metal ceiling with LED panels that simulate daylight. You know every face on this ship. You have met every single person. There are perhaps 10,000 of you, and in a community this small, there are no strangers. There will never be a stranger. You will never meet someone you have never seen before. Every person you will ever know, every friend you will ever make, every person you could ever love is already on this ship and has been since the day you were born. Your job has been assigned to you based on the ship's needs and your aptitudes. Perhaps you are a farmer, tending the hydroponic bays. Perhaps you are a technician, maintaining the water recycling systems. Perhaps you are a teacher. Perhaps you are a doctor. Whatever your role, it was not truly your choice. The ship needs what the ship needs, and personal desires are secondary to collective survival. You will do this job for the rest of your life, or until the ship decides you are needed elsewhere. You will eat what the ship provides. The menu rotates on a 6-week cycle. You have memorized it. You will never taste chocolate, because cacao trees are not efficient enough to warrant the space. You will never taste beef, because cattle require too many resources. You eat algae-based protein supplements, hydroponically grown vegetables, and lab-cultured mycoprotein. It is nutritious. It keeps you alive. It has not surprised you in years. You will never travel. You will never take a vacation. You will never see a new landscape. You will never visit a different city. There are no cities. There is this ship, this corridor, this room. This is your world. This has always been your world. This will always be your world. You will die here. Your children will die here. And the destination, the planet that this whole enterprise is supposedly headed toward, the planet that your ancestors sacrificed everything for, is still 150 years away. You will never reach it. Your children will never reach it. Even your grandchildren probably will not reach it. The destination is not a destination. It is a myth. An article of faith. A story you tell yourself to give meaning to a life that otherwise feels like an elaborate exercise in futility. How do you feel? What is your mental state? How is your sense of purpose? Your motivation? Your will to live? This is the psychological reality of a generation ship. And it is, according to many researchers, the single greatest threat to mission success. Not mechanical failure, not radiation, not disease, the human mind, the crushing, relentless, inescapable weight of confinement, monotony, and meaninglessness. The knowledge that you are trapped, that you were born trapped, that you will die trapped, and that none of it was your choice. We have some data on what happens to the human psyche in confined, isolated, high-stress environments, though nothing that comes close to the duration and severity of a generation ship. Studies from Antarctic research stations, submarine deployments, the International Space Station, and various isolation experiments have documented a range of psychological effects. Depression is common. Anxiety is pervasive. Interpersonal conflicts intensify dramatically, even among carefully selected and trained professionals. The phenomenon known as third quarter syndrome is well documented. Roughly 3/4 of the way through an expected confinement period, morale typically reaches its lowest point. People become irritable, withdrawn, paranoid, and hostile. Sleep disorders emerge. Cognitive performance declines. Motivation collapses. On the ISS, astronauts typically serve missions of 6 months to 1 year. They are carefully selected for psychological resilience, extensively trained, and constantly supported by mission control on the ground. They know exactly when they are going home. They can see Earth through the window. They can talk to their families. They have new supplies arriving every few months. And despite all of this, psychological challenges are one of the most significant concerns of long-duration spaceflight. NASA and other space agencies invest enormous resources in crew psychological support. Now imagine a situation where there is no mission control, no resupply, no going home, no end date. Where the mission lasts not 6 months but 600 years. Where the crew is not a handful of carefully selected astronauts but 10,000 ordinary people, including children, elderly, and individuals with varying levels of psychological resilience. The monotony problem alone could be devastating. Human beings are hardwired to seek novelty. Our brains are stimulated by new experiences, new environments, new people, new challenges. The dopamine system, which drives motivation and reward, is activated by novelty and prediction error, the difference between what we expect and what we experience. In an environment where every day is essentially the same, where the routine never changes, where there are no new places to go and no new things to discover, the brain's reward system slowly starves. This is not a metaphor. This is neuroscience. Without novelty and stimulation, the brain literally becomes less responsive to reward, leading to anhedonia, the inability to experience pleasure. This is one of the core symptoms of clinical depression. And it can become self-reinforcing. The less pleasure you can experience, the less motivation you have to seek it, the less you experience, and so on in a downward spiral. Virtual reality has been proposed as a solution, and it is perhaps the most promising one. If you cannot give people new physical environments, you can give them new virtual ones. Imagine Generation ship inhabitants able to put on a headset and experience walking through a forest, standing on a beach, climbing a mountain, exploring a city they have never seen. The technology to create convincing virtual reality environments already exists in primitive form and will undoubtedly advance enormously in the coming decades. For a Generation ship, VR could be not just entertainment, but essential psychological medicine, a way to give the human brain the novelty it craves without the physical space that the ship cannot provide. But VR comes with its own risks. What happens when the virtual world is so much more appealing than reality that people stop wanting to return to the real world? What happens when people become addicted to virtual experiences and neglect their duties on the ship? What happens when children who grow up spending more time in VR than in reality become unable to function effectively in the real world of the ship? Virtual reality could be a lifeboat for the mind, or it could be another trap. Social conflict on a Generation ship would be unlike anything in human history. Because of one unique and terrible feature, there is no escape. On Earth, if you have a conflict with someone, with a neighbor, a co-worker, a family member, you have options. You can move to a different neighborhood. You can change jobs. You can create physical distance. Even in prison, transfers are possible. On a Generation ship, there is no escape. The person you hate lives down the corridor. You will see them every day for the rest of your life. Your children will see their children every day for their entire lives. Grudges do not fade, because the people you grudge against are always there, always visible, always inescapable. Feuds between families or groups could persist for generations, growing in intensity, eventually threatening the social fabric of the entire community. Murder is particularly problematic. On Earth, murder is a crime that affects primarily the victim and their immediate circle. On a Generation ship, every human life is a precious resource. The ship has a limited population, and every person who is killed or who kills represents a loss, not just of an individual, but of their potential offspring, their skills, their labor, their genetic contribution to the gene pool. But you also cannot simply tolerate murder, because doing so would destroy the social order. So what do you do with a murderer? You cannot imprison them for life, because prisons waste space and resources and remove a potentially productive individual from the workforce. You cannot execute them, because that reduces the population further and eliminates their genetic material. You cannot exile them, because there is nowhere to exile them to. You might confine them, assign them to supervised labor, or medicate them, but none of these solutions is entirely satisfactory. The criminal justice system on a Generation ship would need to be fundamentally different from anything we have ever developed on Earth, and there is no guarantee that a workable system can be devised. The concept of cathedral thinking is often invoked in discussions of Generation ships. Medieval cathedral builders worked on projects that took 100, 200, even 300 years to complete. The builders who laid the foundations knew they would never see the completed cathedral. They built anyway, motivated by religious faith, community pride, and a sense of contributing to something greater than themselves. The Generation Ship is the ultimate cathedral project, a multi-century endeavour where only the final generation sees the result. Can humans sustain this kind of multi-generational commitment? History suggests maybe, but with enormous difficulty. Cathedrals were built in the context of larger societies. The builders had lives outside the building project. They had families, communities, diverse experiences. Their contribution to the cathedral was one part of a rich and varied life. On a Generation Ship, the cathedral is your life. There is nothing else. Your entire existence is the project. You are not a person who happens to contribute to a multi-generational project. You are a component of the project. Your life has meaning only insofar as it serves the mission. That is a fundamentally different psychological situation from the cathedral builders, and it is not at all clear that human beings can tolerate it. What gives life meaning? This question, which has occupied philosophers for millennia, becomes urgently practical on a Generation Ship. On Earth, people find meaning in many ways, through relationships, through work, through creativity, through spirituality, through connection to nature, through travel and exploration, through community engagement, through the pursuit of personal goals and dreams. Some of these sources of meaning can exist on a Generation Ship. Relationships, obviously, work to some extent, creativity certainly, spirituality potentially, but many of the most powerful sources of meaning would be absent. Connection to nature, to the natural world of a living planet, would be reduced to parks and gardens and simulated environments. Travel and exploration would be impossible. Personal goals would be constrained by the ship's needs. The sense of contributing to the broader human story would be complicated by the knowledge that the broader human story is happening light years away, on an Earth that you have never seen and that has probably forgotten about you. Religious faith is frequently cited as a potential source of meaning and social cohesion on a Generation Ship, and there is good reason for this. Throughout human history, religious belief has provided individuals and communities with a sense of purpose, a framework for understanding suffering, a moral code, a social bond, and hope for the future. On a Generation Ship, where suffering is abundant and hope can be hard to maintain, religion could be a powerful stabilizing force. But religion on a Generation Ship could also be a destabilizing force. What if a religious sect forms that opposes the mission? What if a group comes to believe that the destination does not exist, that the journey is punishment for some ancestral sin, and that the correct response is not to continue the mission but to repent and turn the ship around? What if a messianic figure arises who claims divine authority and uses it to seize political power? What if competing religious groups clash, turning theological disagreements into sectarian violence? History is full of examples of religious conflict tearing societies apart, and on a Generation Ship, the consequences of such conflict could be fatal. Let me take a moment to discuss something that science fiction has explored but that scientists take seriously: the forgetting problem. This is the scenario, pioneered by Heinlein and explored by many others, in which the inhabitants of a Generation Ship forget that they are on a ship. This sounds implausible, perhaps even ridiculous to us. How could people forget something so fundamental about their situation? But consider the dynamics. The original passengers, Generation 1, know exactly where they are and what they are doing. They remember Earth. They made the conscious choice to leave. They understand the mission. Generation 2 was born on the ship, but was raised by people who remembered Earth. They have heard the stories. They have seen the photographs. The mission is real to them, though less immediate than to their parents. Generation 3 was raised by people who never saw Earth themselves. The stories are becoming second-hand. The photographs are becoming artifacts. Generation 4 is another step removed. And so on. With each generation, the direct connection to the origin and the mission fades. If knowledge is not aggressively, deliberately and systematically maintained, it degrades. This is how oral traditions work on Earth. Over generations, stories shift, details change, facts become legends, legends become myths. Now add to this the psychological dimension. For a person born on the ship, the mission is abstract. They have never seen the destination. They will never see the destination. The departure happened before they were born. The mission is something they are told about by older people, based on what older people told them. If the educational system falters, if a generation of teachers does a poor job of transmitting the knowledge, if a cultural shift causes people to reject the official history, the connection can break. And once it breaks, it might be very difficult to repair. The ship's database might contain all the original information, but if people do not believe it, if they regard it as propaganda or mythology, having the information available does not help. The forgetting problem is particularly acute when it comes to technical knowledge. The ship is an enormously complex machine that requires constant maintenance by people who understand how it works. If a generation fails to adequately train the next generation of engineers, technicians, and scientists, critical knowledge could be lost, and once it is lost, the ship's systems begin to degrade. A machine that is maintained by people who understand it can last indefinitely. A machine that is maintained by people who follow rituals they do not understand will eventually fail, because they will not be able to diagnose and fix novel problems. This is the cargo cult scenario. The inhabitants maintain the ship's systems by rote, performing actions they have been taught without understanding the underlying principles. When something unexpected happens, something that was not covered by the rote procedures, they are helpless. This is not hypothetical. Knowledge loss has happened many times in human history. The fall of the Roman Empire was followed by centuries during which much of the technological and intellectual achievement of the classical world was lost or forgotten in Western Europe. The construction techniques for Roman concrete, for example, were not rediscovered until the modern era. The Antikythera mechanism, an ancient Greek mechanical computer of extraordinary sophistication, represents a level of mechanical engineering that was not matched for over 1,000 years after its creation. Knowledge is fragile. It requires constant effort to maintain. On a generation ship, where the entire enterprise depends on the continued maintenance of complex technological systems, knowledge loss could be fatal. Now let us escalate from psychology to sociology, because individual psychology, as important as it is, operates within a social context, and the social dynamics of a generation ship would be unlike anything human beings have ever experienced. The question of governance is perhaps the most fraught. How do you govern a community of 10,000 people sealed in a metal box for centuries? Every form of government that humanity has ever tried has significant drawbacks, and most of them have, at some point, failed. Democracies can become fractious, polarized, and paralyzed by partisan conflict. They are vulnerable to demagogues who exploit divisions for personal power. Autocracies can be efficient but are vulnerable to incompetent or malicious leaders, and they tend to breed corruption and resentment. Theocracies can provide social cohesion but suppress dissent and innovation and are vulnerable to extremism. Technocracies, ruled by the technically skilled, can be effective at managing complex systems, but tend to alienate those who are not in the ruling class and can become detached from the needs and desires of ordinary people. On a generation ship, the governance system must achieve several things simultaneously. It must ensure the continued operation and maintenance of the ship's systems. It must manage resources fairly and efficiently. It must resolve conflicts without allowing them to escalate into violence. It must maintain social cohesion across generations. It must preserve and transmit knowledge. It must manage reproduction and population levels. It must maintain morale and a sense of purpose. And it must do all of this for centuries, adapting to changing circumstances and evolving social dynamics without ever failing catastrophically. A single period of truly bad governance, a tyrant who seizes control, a civil war, a collapse of social order could doom the mission. And human history provides no example of any governance system that has been consistently competent and stable for the length of time a generation ship journey would require.